we studied the Green's functions and some details how this can be linked to the solution to the approximating function that we were looking towards the learning problem. Now, going in the same sequence, let us study regularization networks. That means, instead of having a Gaussian based unit in my hidden unit of my RBF network, I replace it with a general Green's function unit. Okay. And let us make some simplifications how we can arrive at this network. The idea of Green's functions g of x comma xi centered at xi gives us a feel of the network structure. It is very important. There is one hidden unit for each data point xi, I equals 1 to n, and the output of the hidden unit is basically g of x comma xi, and the output of the network is this function f of x by combining these Green's functions that are centered at the data points. Okay. So, let us sketch how this sort of looks. We have x1, we have x2, like this we have points xm, and this is like our input layer. So, I just put these units here. Then I have my hidden units comprising of Green's functions. So, I put an edge connecting all my inputs. Okay. So, if I want, I can remove this square here. It is just redundant because we can treat this as we are sensing some inputs, and this is fully connected, and this forms the hidden layer of n Green's functions. And at the output, I linearly combine all my Green's functions through weights W1 through W capital N, and that gives me my approximating function f of x, and this is the output layer. Okay. So, there is one hidden unit for each data point xi, and the output of the ith hidden unit is basically this Green's function g of x comma xi. So, for the ith hidden unit, the output is g of x comma xi. Now, from what we saw through our RBF network, we can impose certain constraints on the Green's functions. By imposing certain constraints, such as positive definite property and making G, this Green's function, to be rotationally invariant, we get the Gaussian form. And this Gaussian form is used in RBF networks. And that is the reason why it is a radial basis function. So, just to recap and sketch this network, we have x1, x2, so on till xm. These are my inputs. And from each of these inputs I connect them to the RBF units comprising of these functions phi, which take this Gaussian form, and this network is fully connected. Okay, and then I have at the output I combine all these outcomes from the all these outputs from the RBF units, and I can also bring in this bias and that is my output unit. Okay, this is my hidden and this is my input. So, the only difference was, instead of having a general Green's function, I have G to be represented by phi, which is basically acting on the norm of the vector x minus xi. Okay, that is the key difference. Now, let us see this from approximation theory point of view, what desirable properties we need for this regularization network to have, right. We need some desirable properties. I will list 3 of them here. So, from an approximation theory perspective, the regularization network has 3 desirable properties or 3 interesting properties. First is, it is a universal approximator. which means it can approximate any multivariate continuous function pretty well, which is what we want. Second, since the approximation scheme is derived from regularization theory and linear in the unknown coefficients, the unknown nonlinear function can always be approximated using an appropriate choice of coefficients. So, an important detail. So, let me write this up. Since the approximation scheme is derived from regularization theory and linear in the unknown coefficients. This is very important, because if it is not linear in the unknown coefficients, then we will have to look at some nonlinear solution techniques, and that can become quite complicated. So, since it is linear in the unknown coefficients, the unknown nonlinear function can always be approximated through an appropriate choice of the weights, right, these coefficients, through an appropriate choice of the coefficients or the weights that combine these outcomes from the hidden units. Last, the solution computed by a regularization network is optimal, right. The solution computed by a regularization network is optimal, and it is based on minimizing a functional that tells how the solution differs from the training examples subject to certain regulatory conditions that depend on the geometry of the problem. So, these three important properties are endowed within regularization networks. Okay. So, I just sort of would recall, one, it is a universal approximator. This is very important, because we saw MLPs as universal approximators. We also saw that RBFs are universal approximators. So, they can approximate multivariate continuous functions pretty well, and the approximation scheme is derived from regularization theory and linear in the unknown coefficients that can be appropriately solved, and the solution itself is computed based upon minimizing a functional, and this is the Tikhonov functional, and therefore it is optimum. So, therefore, this is a desired property. Okay. So, with this we will end this module, and we will work further.